Welcome to Math Zone African Motives. In today's tutorial, we're going to dive into Unit 4.2, Algebraic Graphs. Specifically, our focus will be on understanding and sketching a fascinating type of curve called the non-rectangular hyperbola. By the end of this session, you will be able to identify the general form of a non-rectangular hyperbola, analyze its key features, and confidently sketch its graph. Our learning objectives are to identify the general form, list the features, and sketch the graph of a non-rectangular hyperbola. Let's get started. First, let's establish the fundamental building blocks of a non-rectangular hyperbola. The general form of its equation is x squared over a squared minus y squared over b squared equals 1. Let's repeat that. X squared over a squared minus y squared over b squared equals 1. This specific structure tells us a lot about the hyperbola's shape and orientation. Now let's look at its key features. The first thing to know is that it's an asymptotic graph. This means it approaches certain lines, called asymptotes, but never actually touches them. Another crucial feature is where the graph intersects the x-axis. These points are called the vertices. For a hyperbola in this form, the vertices are located at positive a and negative a on the x-axis. This value a is key to determining the graph's width. Next, let's talk about the asymptotes. These are the guidelines for sketching the hyperbola. Their equations are y equals b over a times x, and y equals negative b over a times x. An easy way to think of this is that the asymptotes are the diagonals of a special rectangle we can draw. To understand this better, let's look at the standard diagram. Imagine a rectangle centered at the origin, with its vertical sides passing through the vertices. X equals negative a and x equals a, and its horizontal sides at y equals negative b and y equals b. The lines that pass through the opposite corners of this rectangle are our asymptotes. The hyperbola branches then approach these dashed lines as they extend away from the vertices. Now that we've covered the shape, let's detail the mathematical features of this type of hyperbola. First, the graph is a relation. This is an important distinction. A relation is a set of ordered pairs, and it doesn't have to pass the vertical line test to be called a relation. In fact, a vertical line would intersect the hyperbola's branches twice, so it is not a function. Second, the graph is discontinuous. The two separate branches of the hyperbola are completely disconnected from each other. There's a gap between them, which is the space between the vertices, from negative a to a. Third, let's talk about the domain. The domain represents all possible x values. As we can see from the graph, the hyperbola exists for x values less than or equal to negative a, and for x values greater than or equal to positive a. We can write this formally as the set of all real numbers x such that xn is less than or equal to negative a, or x is greater than or equal to a. Fourth, let's consider the range. The range includes all possible y values. Looking at the graph, the branches extend infinitely upwards and downwards. This means that the hyperbola covers all real numbers on the y-axis, so the range is simply all real numbers. Fifth, the graph is symmetrical. As you can see, it's perfectly balanced. It's symmetrical with respect to the x-axis, meaning if you fold it along the x-axis, the two halves match up. It's also symmetrical with respect to the y-axis, meaning if you fold it along the y-axis, the two branches match up. Finally, the graph does not have an inverse function. We already noted that it's a relation, not a function. For a relation to have an inverse that is a function, the original relation must pass the horizontal line test. Since a horizontal line can intersect the hyperbola twice, it fails the test, and its inverse is not a function. With that theory established, let's now apply it to a concrete example. We'll follow a step-by-step process to sketch a non-rectangular hyperbola. Here's our question. It asks us to sketch the graph of the equation 16x squared minus 576 equals 36y squared, and then to state the domain and range. Before we can do anything, we need to get our equation into that standard general form. X squared over a squared minus y squared over b squared equals 1. Our first step is to rewrite the given equation, 16x squared minus 576 equals 36y squared, into the standard form. This involves rearranging the terms so that the x term and y term are on one side and the constant is on the other. Let's start by adding 576 to both sides, which gives us 16x squared equals 36y squared plus 576. Then, to get the y term on the same side as the x term, we'll subtract 36y squared from both sides. This gives us 16x squared minus 36y squared equals 576. Now we're close, but the right side is 576, not 1. To make it 1, we divide every single term in the equation by 576. Remember, you must divide everything to keep the equation balanced. Let's simplify. 16x squared over 576 becomes x squared over 36. 36y squared over 576 becomes y squared over 16. And 576 over 576 is 1. So our equation in general form is x squared over 36 minus y squared over 16 equals 1. This is the equation we will work with. Now that we have the equation in standard form, x squared over 36 minus y squared over 16 equals 1, we can easily identify our key values, a and b. Recall the general form is x squared over a squared minus y squared over b squared equals 1. By comparing the two equations, we can see that a squared is equal to 36 and b squared is equal to 16. The value a tells us the distance from the origin to the vertices, and b helps us find the asymptotes. To find a and b, we just need to take the square root of both sides. The square root of 36 is 6, and the square root of 16 is 4. So we have a equals 6 and b equals 4. These are the two essential numbers we need to sketch our graph. With a and b known, we have all the information we need. The vertices are at plus and minus a on the x-axis, so that's at x equals negative 6 and x equals 6. The asymptotes will have slopes of plus and minus b over a, which is plus and minus 4 over 6, or plus and minus 2 over 3. Now we are ready to draw the graph. Okay, let's put it all together and sketch our hyperbola. First, we need a coordinate plane. We'll start by drawing our x and y axes intersecting at the origin. Remember, a is 6 and b is 4. First, we locate the vertices. Since a is 6, the vertices are at x equals negative 6 and x equals 6. Let's mark these points on the x-axis. Next, we'll use the value of b, which is 4. We mark points on the y-axis at y equals negative 4 and y equals 4. These are not part of the hyperbola itself, but they help us draw our guide rectangle. Now, draw a dashed rectangle that passes through these 4 points. Negative 6, 6, negative 4, and 4. The corners of this rectangle are 6, 4, 6, 4, 6 or 4, and 6 to 4. The asymptotes are the diagonals of this rectangle. Draw 2 dashed lines passing through the origin and the opposite corners of the rectangle. These are your asymptotes. The one with a positive slope is y equals 2 to 3x, and the one with a negative slope is y equals negative 2, 3x. Finally, we can draw the hyperbola. Start from the vertices we marked at negative 6 and 6 on the x-axis. Draw curves that open outwards towards the asymptotes. The curves will get closer and closer to the asymptotes, but will never touch them. And there you have it, the sketch of the non-rectangular hyperbola. The last part of our problem is to state the domain and range. This is straightforward now that we have the equation in standard form and a visual representation. Let's first determine the domain. Remember the general form we established for the domain? It's all real numbers x such that x is less than or equal to negative a, or x is greater than or equal to a. In our specific problem, we found that a is equal to 6. Substituting this value, the domain becomes all real numbers x, such that x is less than or equal to negative 6 or x is greater than or equal to 6. This confirms what we see in our sketch. The graph only exists to the left of x equals negative 6 and to the right of x equals 6. Now for the range. The general form for the range is simply all real numbers y. As we can see from our graph, the two branches extend infinitely upwards and downwards. This means the hyperbola covers every single value on the y-axis. Therefore, the range is all real numbers. Let's write that out formally. The range is the set of all real numbers y. Let's quickly check the provided memo. The memo states the domain and range exactly as we have calculated them. The domain is x equals 6, and x is 6, xr, and the range is 4y, yr. Everything matches perfectly. Let's quickly recap what we've accomplished in this tutorial. We started by identifying the general form of a non-rectangular hyperbola. This form, x squared over a squared minus y squared over b squared equals 1, is the key to understanding the graph's properties. We then discussed its features, such as it being a relation, being discontinuous, and being symmetrical about the axes. We also learned how to determine its domain and range. Finally, we walked through a step-by-step process for sketching a hyperbola from a given equation. This process involved rearranging the equation, identifying A and B, locating the vertices, drawing the guide rectangle, sketching the asymptotes, and finally, drawing the hyperbola branches. Understanding these steps and the key features will allow you to confidently work with non-rectangular hyperbolas. Thank you for joining us today. Subscribe for more tutorials from Math Zone African Motives. See you next time.